Greetings, my name is Andrew Olney, and my talk is assessing readability by filling closed items with transformers. So what is the point of reading? Well, it's to understand the text. So we have a text, and we have a reader who constructs some mental representation of it. And we can assess that understanding or mental representation with some task, e.g. questions about the task. Using that understanding, we can talk about readability and reading skill. So when the understanding is good, as measured by the task, we say that the text is readable, or the text difficulty is less than the reader ability. When the understanding is bad, we say the text is unreadable, or the text difficulty is greater than the reading ability. So text difficulty and reader ability are often defined in terms of each other. This framing of readability and reading skill aligns quite naturally with norm reference tests, which compare a reader to previous readers measured by some task. So for example, suppose we have readers at different grade levels that read a text. If there is no difference in text understanding across the grade levels, then we say that either the text is too easy or the text is too hard. If there's a difference across grade levels, it identifies text difficulty. And you can visualize that with this kind of sweet spot, Goldilocks. It's either too hard or too easy, and what you want is something in between. So far, so good. So the question then is what task to use to measure this. So there are many choices, the most popular being questions, which we can divide into recognition-oriented, so multiple choice comprehension questions, sentence verification task, did you read the sentence or not, 50% distractors present, or an inference verification task, is the sentence true based on what you read, again, 50% distractors. These are all common choices. The other group is recall-oriented questions, so short answer questions, or essay questions. The problems with these are that they confound text difficulty with question difficulty. So if especially the recognition ones confound, they engage lots of additional extraneous processing. And then the recall items are additionally hard to score. So closed items are a way of solving these problems or addressing these problems. So here's an example. So the blank is a small crepuscular fox native blank, the deserts of North Africa, ranging from Western Sahara to the Sinai Peninsula. So the first blank captures knowledge and vocabulary. This is actually the fennec fox. The second blank is the word to, and that captures grammar. So if we delete every fifth word, then we get something that mixes these two things, mixes knowledge and vocabulary type blanks with grammar type blanks. So this in particular, this is called nth deletion. And this in particular is every fifth word. So the advantages of closed items like this are that they're very easy to create, like nth deletion is very easy to create. And then the correctness of these has been shown to correlate with comprehension, questions, aptitude tests, etc. There's no confounding of question difficulty and text difficulty. So the disadvantage of these is that it requires human subjects data collection to basically come up with a sense of how difficult something is, which is kind of shared really with the questions on the previous slide as well. So readability metrics were created to kind of get around this issue of needing human data collection. So they were developed based on previous human data collection of close, completion, comprehension questions, etc. They worked directly on the text, and they used historically very basic features. So average sentence length in words, which I'll abbreviate as ASL throughout, average word length and syllables, which I'll abbreviate as AWL throughout, and then word frequency. And examples of this are Flesch reading ease, which uses ASL and AWL, Dale-Child readability, which basically uses the same with a little twist, and Lexile, which uses ASL and word frequency. So metrics like this have existed for over 100 years, and they work really well, and they're very hard baselines. It's quite hard to improve upon these. And people have tried for many, many years to do so. So what can we do? So enter transformers. So it turns out that the Cloze task has actually been used in deep learning for a bit, for a few years at least, but with a different name, and that name is mass language modeling. And the idea here is that the neural network is being trained to reconstruct the text. So you take the text and you delete some things and ask it to fill it in. The text becomes its own training data. That's why it's called self-supervised. But one difference is that these closed positions in deep learning are typically chosen randomly. So this kind of approach to readability has been tried once before. Benzara and Yvonne previously used a model called GPT-2 to look at this connection with closed difficulty and readability. The problem with GPT-2 is it only predicts words to the right, and it's not the same as the closed task because the blank can be anywhere in the interior of the sentence. So it's not really a very good fit. So one of the main questions for this talk and this paper are how do transformer closed scores, which more closely align with the human closed task, actually align with closed difficulty for human subjects collection, grade level readability, and then standard readability metrics. So that's what we're going to be looking at. And the method is to use a transformer called T5, the text-to-text transformer. And the way that this is used is we're going to use 125 word chunks, 2 of those to add up to 250 words. This gives us comparability with the number of words used in our first study, human subjects data collection study. We had to divide it into 2 for technical reasons. It's a limitation of the model. We used rotating nth deletion, where n equals 5. So first we would blank the first word, and then the word 5 later, right, and do that all the way through. And then we would start on the next word and blank it through. So by the time you've done this, you've blanked out every word, right? So every text was processed 5 times, and those were averaged together. Use beam sampling, beam, and then regular sampling to generate the predictions. Scoring that we looked at was correct at 1. So the first thing the network predicted, we scored as correct, or we said it was incorrect, or correct at any weighted by rank of the prediction. It turned out that those 2 were very, very similar. It was usually correct at 1 or not correct at all. So what I'm going to show you just used the beam sampling, which was the first prediction, and then the correct at 1 scores. So that simplifies things and makes it very repeatable. For the baselines, we use Flesch reading ease, AWL, and ASL, which are the components of Flesch. And the data that we used were the Bournemouth passages from 1971. These are human closed scores, pre-post test scores, and reading time. The one-stop English corpus, which is kind of like a ESL corpus for learning English. It's got 3 grade levels and expert assigned difficulty. And Newsella, which is the same kind of thing, but now it has 12 levels, or actually 11 levels of expert assigned difficulty. So let's start with the Bournemouth passages. So there were 32 passages. These were downsampled by Bournemouth in 1971 from a larger study of over 300. I actually went to his 1971 technical report to pull out this data, so it's quite amazing that it was in there. There are 8 levels of difficulty, and each level had 4 example texts. And there was a strong correlation between the T5 predictions and the human close score, the human close difficulty. So it was 0.8. And here's a plot of that. So you can see that there's, first of all, a pretty good trend line. You can see here on the y-axis, this is the human close score. And you can see how separable it was to humans in the first place. So let me get a little pointer here. So you can see that these are the hardest texts, right? And you expect them to be about in a line for the human, and the next, and the next. Interestingly, for the human, it starts to get a bit muddled up right in here, even still before becoming kind of clean again at the easiest level. So for T5 predictions, if you look this way, it tends to spread out the difficulty. So these grade level equivalence classes in human terms get smushed out a bit. But in general, the separation is decent, and the correlation is quite good. So that's nice. So we can look at this in more detail. So the correlation matrix between the various measures, so both the human measures and also the various metrics. So in this top grouping here, pre-post reading, close, pre-post read, those are the human measures. And you can see they're all highly correlated with each other. If we come down here and we look at the readability metrics, including T5 on the last row, we can see that they, in general, are kind of comparably correlated with the human scores, except for the human post-test, which is a bit interesting. And so the T5 is a little bit less correlated with that, what humans learned after reading the text. And then if we come down here, we can look at how T5 is correlated with ASL and AWL. And we can see that T5 is much more correlated with ASL than AWL, but quite correlated, strongly correlated with both. So to investigate the utility of T5 in predicting human close scores, we created some linear models. And so here are those models. So each one of these rows is a different model. And the model is so named with what what predictors are in it. So the first model has everything in it. And you can see that that is better fit than just Flesch. And then Flesch is using these components, and it's weighted according to the model, so it's weighted to the data. So, you know, it's maybe not entirely fair comparison because the all model has one more predictor, has one more feature, but even still adding it improves R squared. We can also try to create more comparable models by using just two predictors, like Flesch has two predictors. So if we use T5 with just one other predictor, and we can see if we do that, then it's about the same as Flesch. It's only 0.01 different. So kind of interesting. Looks like we can get some improved predictive performance using T5, and it seems to be replacing average word length in this formula. So let's look at our next corpus. So that's the one-stop English corpus. I'm going to spend a little bit less time on setup here and just go straight to the results. So if we look at the correlation matrix, this is going to be the only one I show you where not everything is significant. So you can see that T5 is no longer significantly correlated with ASL and AWL, even though it is significantly correlated with ease. So that's interesting. All of a sudden, things have changed quite a bit. Now, recall that on the last slide with Bournemouth, we were looking at cloze difficulty. So humans were actually trying to guess the word in these cloze items. This is no longer the case for one-stop English. Here we're looking at expert assigned difficulty on 3 different grade levels. So this is no longer comparing to cloze task performance. Again, we can build a regression model. And here we can see that, again, including T5 as a predictor improves the R squared. And again, if we balance the number of predictors and only use 2 and compare directly to Flesch, then it is only a difference of 0.01. So we're getting the same kind of pattern as we got before, even though the correlations are weaker and kind of problematic that it's no longer correlated with ASL and AWL. The final corpus that we'll look at is Nuzella. Again, here's the correlation matrix. This time, everything is significantly correlated. It's now moderately correlated with ease instead of modestly correlated. And again, it's more correlated than ASL and AWL. And if we go to the linear models, we can see that now adding T5 does not improve R squared. It's about the same no matter what we do, which is kind of interesting how that plays out. So what we've got here is some consistencies and some maybe inconsistencies across these data sets. And I've put that all together here in this table for easier comparison of what's going on. So these three different corpora represent three different genres. So One Stop English and Newsella are both news corpora, and Bournemouth is academic. Also, One Stop English and Newsella both use this metric of expert ease. So an expert has decided how difficult it is, probably informed by readability metrics, whereas Bournemouth is an actual human subjects data collection to determine difficulty. And we can see here some very big differences in range. So Bournemouth ranges from 1 to 190 in terms of difficulty scores, human difficulty scores, whereas One Stop English and Newsella are like grade 1 to 3 kind of. It's advanced, intermediate, and beginner for One Stop English, and Newsella is grades I think 2 through 12. And I've normalized everything here to start at 1, so you can see that a little bit more easily. So those are the differences, and we can see that consistently across these studies, T5 is correlating with the measure. So these are all significant correlations. So T5 is always correlating with the measure, whether it's the Cloze score or the expert ease. And we can see that T5 always improves the model over Flesch, or it's neutral, as in the last case. And we also see across all three that T5 plus ASL, or average sentence length, is always about the same as Flesch. So it's very comparable to Flesch when used by itself, or used in that combination. But the inconsistencies that we're seeing here are that the Cloze score performance is generally better than the expert ease in terms of correlation. And we're also seeing that within the news and expert ease corpora, if you compare them to each other, that Newsella has a higher correlation than One Stop English. So it's kind of challenging to try to figure out why, since we don't have that much variability in these corpora. But one potential explanation for this is restricted range. So there's a much greater restricted range for One Stop English than Newsella. But I'm not entirely convinced of that, because the general pattern of correlations is also very different between the two. Recall that for One Stop English, there was no correlation with ASL and AWL. So one of the things that comes to mind that I wonder about when looking at these results is whether the expert ease constructed corpora really are that strongly related to like Cloze-based readability or human subjects data collection. And so, that's really my question here: is expert ease as correlated with Cloze as we would expect it to be? And unfortunately, I have no data to speak to that one way or the other. So kind of wrapping it up and looking forward. So, clearly more validation is needed with human Cloze scores. Just looking at T5 itself, the Bournemouth passages were very useful, great, but for each one of those texts, we were looking at a composite of readability across all the grade levels that he investigated. So it would be obviously much better to be able to look at this, have the granularity of Cloze scores for each individual student on a text. Be much more useful. And then also looking at this question of how expert assigned readability corresponds to Cloze difficulty, because I am questioning if maybe we've drifted when the metrics were created, like Flesch and so forth, if experts just started creating these corpora using those metrics and not actually looking at whether or not their difficulty levels had drifted from real human difficulty. And then also investigating knowledge effects. So the real potential, I think, here with deep learning and using T5 is that these models capture world knowledge. And if we created models with different levels of knowledge, that should match readers at different grade levels quite well. Because Flesch doesn't have that at all, right? It can't tell you, for a fourth grader, what they would get right and wrong. All right, with that, I'll take some questions.